Recap. In the decimal system, there are 10 symbols, 0 to 9, to represent quantity. Binary means 2. So in such a system, there are only 2 symbols. So you have 0 and 1 to represent something. And because there's only 2 symbols, the base of a binary system is in 2. And like the decimal system, it also have a place value. And the place value is represented by the power. 2 to the 0 power is 1, 2 to the 1 power is 2, 2 to the 2 power is 4, and so forth until you have 2 to the 7 power is 128. So like the decimal system, when you start at 10 to the 0, it's 1. Each time you move, increase by tenfold. This place value of 10, when you increase to the next one, is 10 times 10, or 100. And again, from 100 to the next place value, it's by 10. So 10, 100 times 10 is 1,000. In the binary system, same concept. You first start up at 2 to 0, it's 1. And then when you go to the next place value, you get 1 times 2, which is 2. Then you increase, and when you go to the next place value after that, you times 2. So 2 times 2 is 4. So each time you move in a binary system, it doubles. So 1 doubles equals 2. You double that is 4. You double that is 8. You double that 16, so forth. Because a binary system has 2 symbols, 0 and 1, you can use switches or a light bulb to represent the state that a binary system can have. Is 0 or a 1, or a 0 means off and a 1 means on. So if I was to go to 2 to the 0 power and turn the switch on, that means I would have the number 1. And if I was to go to the 2 to the 3rd power and turn the switch on at that place, that means I would have 8. In total, I then would have 9. And if I was to turn the switch on at 2 to the 6th power, and 2 to the 6th power represents 64, or the 6th position of the base 2, then 64, and then you add it, 64 plus 8 plus 1 would be 73. Now you could use such a system to count up from 0. So we have 0, and then if we turn the 0 power on, you have 1, and if you turn the 0 power off and 2 to the 1st power on, you have 2. And then to have 3, you make sure that the 2 to the 1st power, 2 to the 0 power is both on, 3. And then to have 4, and then 5, 6, let me correct that, 6. 6 would be 4 and 2. There you go. 4 and 2. 6. Then 7. Then 8. 9. 10. 11. 12. Oops, that's not 12. 11. And then to have 12, you need 8 and 4. 12. Let's review the binary system. In such a system, there are only 2 symbols, 0 and 1. So the base of a binary system is 2. And each power represents a place value. And because it is in the base of 2, each time you increase its place or the position, you are doubling the value. So 2 to the 0 power is 1. 2 to 1, you times it by 2 is 2. And you increase it 4, 8, 16, 32, 64, 28. And each time you turn on a switch, it means that that place value has a value. So if you turn it off, off means 0. So 1 times 0 is 0. 2 to the 1st power is 2 times 0 is 0. And if we were to turn on, 2 to the 1st power, or 2 times 1 is 2. Because a binary system have only 2 symbols, 0 and 1. Now how can we represent the concept of a on and off, place values, and base of 2 on an actual physical hardware? In subsequent video, we are going to go through the process of taking abstract idea of the binary system to form what is called a half adder and a full adder, And from that concept, you move on to transistors. One last note. There's a reason why I only have 8 switches along with its base and its power. Just like a computer system, each of these switches represents a bit. So I have 1 bit here, 2, 3, 4, 5, 6, 7, 8. Like a computer system, 8 bit equals 1 byte. And 1 byte represents 1 unit. In computer science, data is represents as byte. For example, int or a double word is represented by 4 bytes. 64 or 64-bit is 8 byte. 8 byte means you have 8 of this unit or 8 grouping of this on off switch.